So what is work? Well, first of all, let's talk about two basic things. Work is something done by a given force over some path. All right. And you can do work on a body. Right? So you pick somebody and pick some path, motion, which the body is going over, and then you can talk about the work, which is done by a force on that body. Now, some of you guys may remember a simple case, right? Simplest case. Simple case, if you have a constant force aligned with the displacement, aligned with the motion. So, for example, I've got a box, all right, and I put a force on it, then sometime later, you go over here, later time. So the box has moved to displacement delta R, and the work done is what? Some of you guys had high school physics. You should have this force type of distance. Right. Force times the distance. Now this, of course, assumes that the force is aligned with the motion, right? And it's also constant force. Let's see here. There's a couple of different ways you can generalize this case, right? You can talk about a non-constant force, which is aligned with the force, with the motion, right? So how about that? What if I think about, I've got a box here. Here's f of x1. Then at a little bit later time, the force on the box is f of x2. And let me just illustrate the varying force with varying lengths arrows. And then over here, maybe the force is like this even, force of x3, right? So if you think about a little displacement of the box, in the first two cases I have there, you got like a little positive. If you just think about the box shifting a little bit like that, you could talk about the little amount of work done. The change in work for that piece would be something like f of x1, right? Times the change in x. Or, okay, now I'm saying that I had r over here. I'm trying to be, anticipating something. But you could write x here, right? It's one-dimensional. Wouldn't really change much, right? So that would be positive work, right? On the other hand, here, if I think about going from where I have a picture to where I'm picturing in red right now, right? Then the change in work for this piece, for the work done would be something like f of x3, change in x. It would be a minus, right? Because force is opposite to motion, the negative work. Okay. So if you think about this infinitesimally, you could say dw, although, I'm sorry, but instead of putting a minus here, what can we do? How about we just put a plus here, and then we have a convention. What's our convention? F of x3 is what? Less than 0 because it's pointing, what? To the left, right? Incorrect? So that would be our convention. So in all three of these cases, a little bit of work done, dw, is something like f of x dx, right? If you take the limit as these little displacements get smaller and smaller. That formula makes sense, right? Because if you think about a very, very small displacement, the force is approximately constant, right? I can't just say it's the force times the distance because I don't know which force to pick. The force at x1, the force at x2, the force at x3, it's varying, right? But what I can say is that the little bit of work done from that little dx is just f of x dx, right? And then how do I find the total work in such a situation? Right, I say integral from the starting x to the finishing x, right? F of x dx. That would give me the net work done. Okay, so constant force, same direction, just force times distance. Right? Varying force, same direction, I can integrate. Well, what else can happen? Does your force have to be applied in the direction of motion? Well, no. There's lots of forces which are not, right? Like I could take this chair, for example, and I could push on it like this. I'm putting a force like this, as you can tell from the noise, right? In contrast, if I did like this, that would be more like, that'd be more like these, right? So you can apply forces which are not directly in the direction of motion. So whatever concept we have of work had better address those other possibilities. So to first, the next generalization would be, so varying, not varying, how about constant force? Next case, we could have force constant, but not aligned with motion, right? And so the motion, generically speaking, would be delta R. So in that case, what you do is you say work is equal to the force dotted with the displacement. Where this is that dot product we talked about earlier. So for a given force, you do the most work when you're aligned with the displacement. You do the maximum negative work when you're exactly opposite the displacement at each point along the motion, right? And you do zero work if the force is perpendicular to the displacement. You're like, but how are those motions possible? Like if I push opposite the direction of the motion, how is that motion possible, right? I mean, that's what I think. Well, there's more to the story, right? I'm talking about one force. I'm not talking about the net force, right? So there's more than one force involved in this story. So when I talk about the motion, you shouldn't necessarily think that this motion is due to this force, right? There's more than one force involved. It is, of course, interesting to talk about the net force and the work done by the net force. When we talk about that, we get something called the work energy theorem, which is interesting and I'll prove shortly. Okay, so that's the other case. Now, and then finally, what if the force is equal to a function of where you are, position, right? And it varies direction. All right? So in that case, I argue that what you should think about is dW is equal to f of r dotted with dr. So where dr is like a little displacement, if you want to think about it. So here's my r. And then over here would be f, it would be r plus dr. So if you make that displacement, that little dr small enough, then essentially the force is constant over this little line segment, right? And so to a pretty good approximation, this guy is dr. I mean, I'm writing things infinitesimally. It's not an approximation. This is an exact statement. You could arrive at this from a limiting process looking at delta, like a finite delta r, taking the limit as it goes to 0. I can show you after class if you want. But this is like, that's nice, but what does that actually mean? Like, how do you calculate such a thing? Well, the way to calculate that is in terms of the equations of motion. In other words, the position is a function of time for the particle in question. So in view of the equations of motion, in view of r of t, this we can rewrite as f of r of t dotted with, well, I don't know what dr is, but I do know what dr dt is. What's that? Velocity, right? dt. And so I just divided and multiplied by dt, formally speaking. There you go. That is the infinitesimal work done as you displace from, say, time t to time t plus dt. So to find the total work over, say, some path from, say, time 0 to time 1, the work then is equal to the integral from t1 to t0 to t1 of f of r of t dot dr dt, parentheses, dt. Now, this thing is so important, so special, it has a name in Calculus 3, or in this course. This is called the line integral. Now, it's an interesting piece of mathematics that the line integral over the curve, C, is independent of the choice of parameterization which is chosen. So I'm talking about the parameterization which is given to us from physics. In other words, the parameter is time. But it is a mathematical fact that if you reparameterize the curve by an orientation-preserving map, in other words, some other path which gives you the same set of points, but perhaps for like arc length or some other, double time or quarter time, whatever, you pick your favorite parameter, it gives you the same line integral. So this thing I've written here is actually geometric. It's independent of time. It really just has to do with the values of the force at each point of that curve. But anyway, that said, a line integral is something that's in Calculus 3, and there's all kinds of handy-dandy theorems which are known for line integrals. Some of them I'll be sharing with you, before you know it. But that is the general definition of work. Okay? So, there you go, definition of work done by F. And as you can see, that covers all the cases that we talked about. Constant, different direction, blah, blah, blah. Varying force. Okay, so let me work a specific example for you guys. In my lecture 15, I actually show you how this formula reproduces the special cases by just looking at specific, specific cases like the force is constant. You're just going along a line, et cetera, et cetera. I actually derive from that definition back to these special cases to show you that it in fact is the same. Probably more useful for us to look at an example which has a little bit more to it. Let's look at the, we're going to set aside units for a bit here if you guys don't mind. I mean, there should be dimensional multipliers in here to make it more physical, but for the sake of math not being too cluttered, let's look at the twisted cubic. T squared, T cubed, and let's say from time 0 to time 1. And let's find the work done by a force. Let's see here, what do you guys want? We need some kind of force. What kind of force do I need? What's that? 40. 40, I'll give you, I'll take your 40. I'll put it here. Anybody else? Something more exciting perhaps?
3.5.
Shadow quotes. Thank you, I'll make that a y squared. And how about x plus z? All right, there we go. So to calculate it, so this is not one of the forces we talked about before, but a force, right? If I write force of x comma y comma z, in Stewart or Hausalas and Hilly, most of the standard books, whatever, I don't know, you have, a lot of times they'll use like p I hat plus q j hat plus r k hat. I might write p x hat plus q y hat plus r z hat. These p's and q's and r's, these are all functions. They're functions of x, y, and z, generically speaking. Okay. So this allows for all kinds of forces, which are, in addition to the ones we looked at already, like gravity and spring, more complicated things, right? Generically speaking, I'd say F is a force field. If you give me a point in space, it tells you the force applied at that point due to this force field. Yeah.
So is that force F of R of T?
That actually is
Just F of X, Y, Z?
Yeah, that's F of X, Y, Z, which I sometimes will just write as F, which is an abusive notation, of course, but.
So how do we convert that to F of R of T?
Indeed, a good question. So F of R of T, in this context, would be F of T, T squared, T cubed. So what that means is you plug in, right? Plug in x equals to t, y equals to t squared, and z equals to t cubed into this formula right here. So 40 is still 40. Sorry, it's kind of not a non-event, but there it is. Constant functions are really easy to evaluate. Y squared. T to the fourth, right? And then I put x is t, z is plus t cubed. Okay, so we're at the moment we want to find the work done by this force over the twisted cubic, all right? And we're assuming it takes a second to travel the twisted cubic, which is the path I wrote up there. So let's see, we've got this piece, right? Now we got to find what's the velocity of the twisted cubic. Yeah, dRdt is just, we can do something 1, 2t, 3t squared. Okay, take it. And then what's the f of r of t dot? F of r of t dot dRdt then is equal to what? Right, so just look above. You've got both of those vectors here. We can take the dot product and write it down, right? I don't need to write it out again. We can just do the dot product in our head, right? Well, I mean, I'm going to. I hope you can forgive me. So I get 40 plus, let's see here, t to the fourth times 2t gives me 2t to the fifth. And this guy and that guy gives me plus 3t cubed plus 3t to the fifth. And here, some strategically placed underlining shows you the source of the terms. Okay. Can we simplify that? I mean, terms collect?
Yes.
Oh, yeah. So what do I got? I got 40. So this is equal to 40. And I'll put the t cubed first, plus 3t cubed, plus 5t to the fifth. Hey, that's cool. That was an accident. Sorry, it amuses me. You'd be like, okay, this is great math and all, but does this have physical significance? In fact, it does. In fact, it does. We will soon, well, you perhaps have heard the slogan before. Work is the ability to do what? Or energy is what, I should say. Energy is the ability to do work, right? So there's a connection between work and energy, right? So if energy is the ability to do work, it stands to reason that this has something to do with energy, right? Because you're integrating over time, you're getting back work. This must be a rate of change of energy, right? In fact, this is the power. In fact, this is the power developed by the force F at time t. This is the power. Or dE dt, the energy free in a time associated with F. At time t. So this thing we're integrating to get the work is the power. Something which we do not emphasize in Calc 3, but it is true. Well, in Calc 3, I can't say that because oftentimes we'll look at curves which are parameterized with respect to arc length or some other thing which does not have the meaning, the physical meaning of time. Here t is time. Okay, then let's calculate work. What do we got? Work. Integral from 0 to 1. I think we can do this integral, right? 40 plus 3t cubed plus 5t to the fifth dt. So we've got 40 plus 3/4 plus 5/6 know. That's a thing. What is that number?
499 over 12.
Oh, okay.
41.
499 over 12, I heard. I'll believe it.
41.58.
40.
It's the
41.58. Okay. Now, I understand many of you have not had calculus 3 yet, right? Not a prerequisite, but I hope you can appreciate I'm showing you how to calculate a line integral. It's very simple. All you need is the formula for the force and the formula for the path over which you're finding the work. And then you just follow this prescription I just showed you. That's it. When you get right down to it, all you have to do is substitute the path into the formula for the force and then integrate. I mean, there's a dot product, okay? You guys know how to take dot products. All right, I'd be happy to do more of these mathematical examples in future lectures if you ask me, but I'm just going to leave it there for now. We're going to go on to the physics, okay? What are the units of work is a very, very good question. So it's even clearer before this. We had things like in a special case when the work is constant, we had force times distance, right? So it's a Newton meter will be the units for work. Now that actually is so important that it gets its own name. A Newton times meter is also known as a Newton meter. You ever notice that we say Pacific Ocean, but we say Lake Erie? Like, we say lake before we say the name, but we say ocean before.
Yeah. We say river afterwards.
Pacific Ocean versus lake.
Except if it's the Rio Grande. That technically.
What about rivers? How do we name rivers?
Grand River.
River Grand.
It's the Rio Grande.
No,
but
Rio
it's-
Grande is Portuguese, which
Well, it's Spanish.
they flip it. They flip it.
It's the Rio Grande, but it's the Amazon River.
But Rio Grande is a great river.
See, this is why I like physics more than English. Physics is logical.
It's the Panama Canal.
All right, anyways.
It's the
That
Bering
said, we
Strait.
still do have names in physics. There's name calling. A joule, a joule is a Newton meter, otherwise known as a kilogram per second squared times meter, aka a kilogram meter squared per second squared. There you go. In fact, that is the unit of energy and hence work. Work is energy in motion.
What would happen if you just multiplied mass by the velocity squared?
And mass. Mass. That's interesting. You have observed that this also would suggest something about, that's actually a very good comment. It says something about mass times velocity squared. There's a significance to your comment, which I will come back to.
Oh, is it
It's actually,
kinetic energy?
that's actually, that is kinetic energy, yes. So yeah, you can see a lot from units if you start looking at them. But I wanted to, here's a nice example, it's kind of silly. Get a box, right? And then you take that box and you move it over to here, like so. All right. So you motion by force, which is tangent to path of length L. If the force of kinetic friction is mu, times the normal force, and work done by friction. What's the work done by friction in this silly example of mine? It's in a plane, all right? So if you just let me pick any particular part of the motion and just kind of expand on that, you've got the force of friction going this way, right? You've got the velocity of the motion, dr dt, going that way, right? I'm not telling you what makes the box move. I'm just asking you about the work done by friction, right? What's the, in this situation, what's the normal force? Just mg, right? There's nothing else. If there's nothing else, I'm assuming there's nothing else. Assume it's, the box is pushed horizontally, right? So the force of friction is just the weight times mu. So then what? What's the power here? Force of friction dot dr dt. Well, it's just what? It's just minus mu mg, right? And so to find the work, I integrate from time 1 to time 2. I'm saying that this is time 1 and the final time is time 2 of minus mu mg dt. What do you get?
What is it minus mu?
Oh, eliminate it. Yeah. So sorry. What am I missing? Let me fix that. Maybe the blank down here beneath. Velocity is what? It's speed times direction, right? So I can write this as the force of friction dotted with the speed times the direction, v times v hat, right? But it's clear that v hat is anti-parallel to the force of friction, right? So what is this? This is just minus mu mg. The speed, that's the right formula to put there. I forgot the speed. My formula before would have only been correct if I was assuming it was moving at unit speed. And I want to assume that. So there you go, there's a speed. Fill in the blank. So let's see here, the calculus isn't that hard. I got minus mu mg integral from t1 to t2 of the speed. What's another formula for the speed? How about the change in the arc length per unit time dt, right? You guys know the speed is ds dt. But what's the integral of ds dt? Right. S of t2 minus s of t1 by the fundamental theorem of calculus. And of course, this is just L. That's the total arc length. So there you go, minus mu mg L. That's the work done by friction, which is totally natural. It's the length of the path times the value of the force of friction, the magnitude, and there's a minus because the friction force is opposite the direction of motion. Which is what you'd expect, right? I mean, if I ask the question, you move the box in a straight line 10 meters, and I tell you the force of friction is 10 newtons, and I ask the work done, you should immediately go minus 500 joules, right? I just took that. Sorry. My brother. Okay, he means well. I probably called him in class, he'd give me back. Math. My younger brother. He works at Appalachian State University in Boone. I'm not sure. I think we're actually colder than them this morning. But they do get more snow. Anyway, my point is a very natural result. Now, okay, so I want to prove something for you. I want to connect this notion of work to the notion of kinetic energy. Okay, so what is kinetic energy? Kinetic energy. can't spell. Energy. Now, depending on who you are, there's different letters that I see people use for this. I sometimes prefer KE, which is kind of obviously kinetic energy. At times I really use T, and I'm feeling more sophisticated. But anyway, whatever floats your boat, it is 1/2 mv squared. So this is the kinetic energy for mass m with velocity v, right? And the magnitude of the velocity is the speed v. So kinetic energy is a scalar. It's a number. If you have the same speed, it doesn't matter what direction the velocity is going in, same kinetic energy. If I throw a ball 10 meters per second up, if I throw a ball 10 meters per second to the left, to the right, at you, whatever, same ball, same speed, same energy, kinetically speaking. Okay? What's the connection between this and work? Well, here's the thing. Consider work done by the total force, or the net force. What makes the net force different than the forces I've talked about so far today? There's one very, very critical difference about the net force and these other forces I've talked about. The net force is subject to Newton's second law. So the net force is connected with the kinematics of the motion. Whereas the other forces I've talked about don't have to be connected with the kinematics directly. All right, but the net force has F equals to ma, right? Or m dv dt, as it will be more significant for us to think about. Okay. So we can calculate the work done by the net force. Let's do that. The net work, as it's called. So that's the integral, say, from time 1 to time 2 of F net dot dr dt dt. All right. So far, that's just the definition of work. Right. Then what? Well, I can use Newton's second law, and I can rewrite the integral from t1 to t2 of m dv dt dot v parentheses dt. So I traded my dr dt for v, just to make everything kind of more in line notationally. Okay? So far, so good? Everybody with me? Okay. Now there's this thing called the product rule. Let's look at it for a second. So what does the product rule say? ddt of v dot v, what is it? It's v dot dv dt plus dv dt dot v, right? In fact, this is a product rule which is known for the dot product. I think I mentioned it earlier this semester, I forget. It's one of my favorite properties of the dot product. I probably mentioned it. If I didn't, I'm so sorry. Hey, I did that. So the dot product is commutative. It's commutative, so this is really twice dv dt dot v, right? So what that means is I can trade this expression here. I can divide this equation by 2, right? And I can just as well write integral from t1 to t2 of m over 2 ddt of v dot v. dt, of course. Or one more step just to clean it up, okay? Of course, this can also be rewritten integral from t1 to t2 of the derivative of the quantity 1/2 mv squared dt. Because v dot v is v squared. Right? Any vector dot itself is the length of the vector squared. That's true for velocity as it's true for anything. Now I'm integrating a total derivative, right? So fundamental theorem calculus part 2 says it's just the difference of the thing which is differentiated. In other words, this is just 1/2 mv squared evaluated from time 1 to time 2, right? Or you could say from velocity 1 to velocity 2. In other words, it's the kinetic energy at time 2 minus the kinetic energy at time 1. And that, folks, is the work energy theorem. The work energy theorem simply says that the net work done is equal to the total change in the kinetic energy over the motion. In the example I just erased, you could ask what the net work was. The net work done by, well, I can tell you more about it. I mean, please just restate it here. So here's the theorem. The net work is equal to the change in kinetic energy. This is the work energy theorem. So let me look at an example. Let's see here. Suppose I have this here, a bunch of notes, all right? I take it here, let's say at position 0, right? And then I raise it. It's right here. Actually, it doesn't really matter how I raise it. I raise it to right here, all right? And suppose I raised it a meter. I don't know, I have no idea, but suppose it was raised a meter. Then I can ask, what's the net work done by gravity? What's the net work done by my arm? All right, going from here to here. Net work done by gravity, net work done by my arm. Okay. So, got book. Book. V1 equal to 0. Let's say V0 equal to 0. V final equal to 0. Right? And let's see here. The force of gravity, what's that look like? We got energy downward, right? And then the lifting force, right? And the lifting force was complicated, right? Depending on how I did it exactly. But the question of what's the net work done by the, what's the work done by lifting force over the motion, there's no ambiguity there. Let me show you why. So the net force is what? And so we're just talking about vertical direction, okay? It's the lifting force, right? That's going up. This is lifting is up minus mg, right? And so to find the net work, I can integrate the net force over dz from, say, z naught to zf, right? What would that be? Integral of the lifting force from z naught to zf dz minus the integral of mg dz from z naught to zf. Now, one of these integrals we can do, right? I'm not even describing for you how complicated the lifting force is. It's very, I can't give you a formula for it. All I know is I'm lifting it from here to here in some way. This I do know. I'm starting from rest and ending at rest. Okay. So I do know the change in kinetic energy over this problem, right? What is the change in kinetic energy?
0.
zero, right? Because it's zero kinetic energy before, zero kinetic energy after, right? So. I could do the same problem where I was moving where the book was moving at constant velocity the whole time, constant speed rather the whole time. And if it's moving at constant speed the whole time, then I also know that the forces balance it at each point. I didn't do that though. So that's zero, right? What's this? This integral you can do, right? That's mgz minus mgz evaluated from z naught to zf, right? So that's equal to minus mg zf minus z naught, right? Or if you like, minus mg change in z. But that shows you then that the work done by the lifting force is equal to mg delta z. Because it has to be, it has to be this plus that has to be zero, right? So whatever this is, it has to be the negative of this. The work done by the lifting force has to be the opposite. So the work done by gravity is negative because the gravity is pointing opposite the direction of motion, right? The work done by my hand lifting the book from the lower spot to the higher spot is positive because my lifting force is in the direction of motion. Does this make sense? Let's see here. Another example that sometimes is interesting to people. Suppose you're moving in a circle, right? And maybe you're swinging. I guess you probably can't. So you got. I don't know, supposed to not that use your imagination. Anyway, he's got a cat, right? So he's taking the cat and he's swinging the thing like it's so fast it's practically horizontal circle, like just round and round and round and round and round and round and round. You know what I'm talking about? The question is, what's the work done on the cat? By Mr. Top Hat. If he's spinning it in a circle, let's say at 3,000 RPM. Keep in mind, Mr. Top Hat is Asgardian. I mean, he has certain privileges. Yeah,
Lucky him.
relative of that the dude with the hammer. I don't know. All right, so here's the speed of the cat. The force is basically being applied by the tension force, right? So the answer is the work being done on the cat by the tension force is zero. Doesn't matter how fast you spin it. Why? Perpendicular. What command is x at? That's right. Perpendicular. So an important example, ignoring cats spinning in circles, there are lots of examples of this in physics. And next semester, we'll learn about a magnetic force. The formula for the magnetic force, looking ahead a bit, will be this. It'll be Q, V cross B, where V is the velocity. So you see that magnetic force is by its very construction built from a cross product with velocity, right? Which means that the magnetic force is perpendicular to the velocity, which means that the dot product of the magnetic force with velocity is automatically zero. So the power developed by a magnetic force is zero. Be like, what's weird? How do you make motors work, right? I don't know, it's a mystery, isn't it? If only you're taking some course where you can figure that out. I mean, maybe next semester. But anyway, just because a force doesn't do work doesn't mean you can't do things with it, right? I mean, yeah, it's not this force isn't doing work, but it is associated with emotion, right? So don't take this slogan that energy is the ability to do work. I mean, you got to be careful about how you make this. You think of it as being equivalent in your mind. That it's not as. When I say work, I'm talking about something technical. when I talk about energy, I'm talking about something with units of joules. I'm not talking about some sort of ethereal, mystical thing that the universe gives back to you. Are you guys like Oprah? Any followers of Oprah in here? I don't know. My old pastor used to talk about Oprah a lot. In terms of the mysticism of Oprah. When Oprah talks about Jesus, she's not talking about the literal historical Jesus. She's talking about an idea of Jesus, a metaphor. You should be aware of that. Some people, when they talk about Jesus, they're not talking about the person, Jesus Christ. They're talking about the idea. In terms of his love and compassion and so forth. Which of course is good. But it's better to know him, right?